In this video, we're going to explore an interesting relationship between one of the most fundamental constants in mathematics and an experiment you can perform at home involving nothing more than a piece of paper and some sticks. We'll also run some large-scale simulations and dive into the underlying mathematics at work. Let's take a look at the setup. Imagine that we have a matchstick of known length, we'll call it L. Now, picture drawing a set of parallel lines each spaced equally from their immediate neighbours at a distance of 2L. The lines will lie on a piece of paper which serves as the boundary of our region. What are the odds that if we toss our matchstick onto the piece of paper, it will land touching one of the lines? Will it be every second match? Maybe every third, fourth or fifth? Or will there be no discernible pattern at all, given that we're tossing them at random? To get a feel for the problem, let's start by throwing just 30 matches onto our piece of paper. We'll estimate the odds of a hit by keeping track of the total number of throws and the number of successes. Let's see what happens. From what we're seeing, it seems like the odds are somewhere between every second to every fifth match landing on a line. However, the number fluctuates quite a bit since we're working with a relatively small number of trials. But what do you think would happen if we toss more matches? Like, a lot more. Will the odds continue to fluctuate or will they converge to a specific value? First of all, let's change our viewpoint since things will get a bit cluttered if we toss 100,000 matches onto our paper. Instead, we'll graph the results. Along the bottom axis, we have the total number of matches tossed, and on the left axis, we have the same odds calculation that we tracked earlier. This time, we're going to check in at 100, 1,000, 10,000, and 100,000 matches. We'll repeat this 5 times to make sure our results are reasonably accurate. We can see immediately that our odds begin to converge, but the most interesting part is the value they converge to. That is, pi. Okay, so what is pi doing here? This seems a bit unexpected since pi often shows up in relation to circles and trigonometric functions. Yet here we are throwing straight matchsticks at random onto a rectangle with straight lines drawn on it. What's going on? Well, let's take a different approach and try and calculate the probability from scratch to make sense of our experimental result. There are quite a number of derivations, but today we'll focus on one that I think is broadly informative and doesn't require too much prior knowledge. We're interested in determining the likelihood that on a given toss the match will land touching a line. In order for that to happen, 2 conditions need to be satisfied. The first condition is that the match must be close enough to one of the lines to actually touch it. The second condition is that the match must be oriented in such a way that it overlaps the line. In order for a success to occur, both conditions have to be met simultaneously. When dealing with the probability of 2 independent events like this, the likelihood of both occurring is the product of their individual probabilities. Looking at the first condition, being close enough to overlap a line, it means the match's center falls within L/2 of a given line. The probability of the match landing in this region is given by the proportion of the feasible area to the total area. For our specific setup, this comes out to be a half, that is, 50% of the time our match will land close enough to potentially touch a line. However, remember that the odds aren't exactly every second match, and that's because of the second condition, which requires that the match be appropriately aligned to create a crossing. This condition is a bit more complicated to resolve analytically. First, we'll consider only the case where the match is within touching distance, since otherwise we have an automatic fail. In this scenario, the center of the match can be located anywhere from directly on the line to a distance L/2 away. Let's zoom in to get a better look. For any spot within this region, there's a cone of sorts describing the possible angles at which the match could land and touch the line, ranging from a single position of perfectly vertical at a distance L/2 to any orientation at a distance of 0. We've established that if our match lands within a suitable distance from the line, some fraction of the possible orientations will result in a successful toss. In other words, we have a probability of success. Let's consider the angle from the vertical to one of the edges of our cone to be theta. Then, anywhere within this suitable distance from the line, our probability of success can be described as the number of successful angles, 2 theta, out of the total possible angles, pi radians, giving us 2 theta over pi. Now we just need to determine what theta actually is. To do this, let's apply some trigonometry. For simplicity, let's assume the distance between each line is 4, though any value will yield the correct result. Our match has a length of 2, making the radius of our sector and hypotenuse of our triangle 1. We'll consider the distance of our match's center from the line to be x. Then, since cos of theta is given by the adjacent over the hypotenuse, our expression simplifies to cos of theta equals x. That is, the angle theta equals inverse cos of x. Now, we can express the probability of success for a given distance x as 2 times the inverse cos of x over pi. Finally, we need to consider this probability across all feasible x values. We can do that by integrating. Recall that the feasible region on either side of the line extends a distance equal to half the length of our match, in this case, 1. So the cumulative probability that our match lands in the correct orientation is given by integrating our expression from 0 to 1. This integral of the inverse cos function is a bit complicated and we won't delve into it in this video, but you can verify online that it does indeed evaluate to 1. Now, remember that the probability of a success is the product of the probabilities of our two conditions. This finally leads us to the result that the probability of our match hitting a line is equal to 1 on pi. With that knowledge, it's interesting to visualize things the same way we did earlier. Once again, we have the number of tosses along the bottom, and on the left, the probability. We see that the probability converges as we would expect for large n values, approaching 1 on pi. Let's consider how we would calculate the probability experimentally. Generally speaking, the probability of an event can be estimated by taking the ratio of the number of desired outcomes to the total number of outcomes. In our case, the number of successes to the number of throws, which approaches 1 on pi. Look familiar? This is just the reciprocal of our odds calculation from the very start, which must, in turn, approximate pi. If you enjoyed this video and want to support the channel, make sure to subscribe and feel free to check out the links in the description below.